Okay. I think everything is set up.
It looks like you have not activated your microphone. Ah,
Is this right? No, that's no.
okay.
Okay. Then, hi everyone. I'm Xavier Ge. So, yeah, thanks for the organizers for organizing this. So today I'm going to be talking about a project I've been working on, formalization of Drin modules. This is joint work with María Inés de Fru Fernandez. Sorry for pronunciation. Yeah, so my plan for today is to kind of give some motivation, try to convince you guys that you should care about ject modules. That's kind of my objective, and then try to define it. Okay, so in let's say simple language, and then I want to talk a bit about the formalization and yeah, kind of what's been happening. And so this is still very much WIP. There's still a lot of work to do, but at least I have the definition that I can show you today. Okay, so what are Drin modules? So according to this TV show, you can shut down reactors with them. Didn't know about that. But and maybe a bit more serious, okay? So I'm going to assume you care a little bit about number theory and you think numbers are interesting, okay? And for example, I'm going to assume you think the Riemann hypothesis and these types of questions are interesting. And with this point of view, I have the function field analogy. So what the function field analogy is pretty much we have these very interesting questions on numbers, like the Riemann hypothesis, and we want, and then we have something that's kind of similar. Here I have polynomials over finite field FQ, and actually these share a lot of similar properties. Okay, it's actually quite interesting. You can really see a clear analogy between the two, just because they're actually a little bit similar. And then you can kind of continue this analogy with other objects starting from the integers, okay? And then if you, from the integers, you get the field, right, which is the rationals for the function that looks like the rational function. So that's ratio of polynomials. And then you have finite algebraic extensions. So if you don't know what that means, it's pretty much you taking extensions of rationals, you're adding, let's say, root 2. Okay, and then you can do the same thing for my field of rational function. And then if you add all of these algebraic stuff, you get the closure, the algebraic closure. You can do that on both sides. Something else that we'll be interested in is some notion of absolute value. So we have the normal absolute value on reals, let's say, on the left, and on the right, that kind of corresponds to this absolute value that I write within an infinity. And this is q raised to the degree of my polynomial, at least for the polynomial. What?
This absolute value infinity alone, does it satisfy the triangular inequality and like that?
Yes. Yes, something actually stronger than that for the function field case. And then the reason I introduced this norm is because then I want to get the completion. On the left, you get the reals. On the right, you get this kind of funky looking thing that's kind of infinite sums, if you want. And then my analog of C, here it's kind of interesting. You need to take the closure and then complete again, okay, to get something that's kind of similar to C. And then you have all of these objects that are kind of matching on each side of the analogy. And I just want to say, what are function fields? They are these finite algebraic extensions of my field of rational functions. So every time I talk about function fields, you can just imagine the simplest case, FQT, okay? So, yeah, so this is an analogy. I said this. And what's interesting is that proofs are kind of somewhat easier in function fields. Okay, so the hope is if it's easier, we can try to prove interesting stuff, maybe carry over the proof on the other side. That could happen. Notably, what's proven over function field, the Riemann hypothesis. Okay, so that's kind of this really cool result. The analog of the Riemann hypothesis that you can, of the Riemann zeta function, sorry, that you can construct over function field. Well, its Riemann hypothesis is proven. Okay, something else interesting, the Lagrange program for GLM. So maybe you've seen these quantum magazine videos about these continents and the bridge that mathematicians are building between these continents and how that's related to Fermat's last theorem. Well, these are statements over, let's say, the numbers, but if you consider the Lagrange program over function field, well, that's also in a lot of generality actually been done. So we have like these big theorems over function fields. Now what I want to talk about is in 1935, okay, Karlitz extended kind of this function field analogy by defining an exponential function that I'm not going to really define here, but that you can think of has a lot of similar properties as the usual exponential function. And it has a difference though, so and that I kind of want to focus on. If you have kind of this action of here where I multiply by some integer n, we know that we can pull it out, okay, on the right side. I can kind of pull it out here as the power of n. If I do this for my exponential function that Karlitz defined, well, we have to think about what is equivalent in function fields. So integers are polynomials. So here I'm multiplying by a some polynomial, okay? And can I pull it out? Yes, but in a rather different way. I'm writing it here C of a, where C of a is some polynomial that is additive. So I can pull it out by just having a power of n, but I still have some relation that allows me to pull it out in a little bit different way. And these are additive polynomial, which we're going to see again. So this kind of mapping is kind of the prototype of what I want to talk about today, the infant module, and it's called the Karlitz module. And it's this action, right, that takes an A, and then you, instead of just multiplying by a polynomial, you really instantiate it as a polynomial. Okay, so there's a lot of polynomial, but by this I mean the A is a polynomial, but the C of A is also this linear polynomial, right? And this is really the module action that we care about. And this defines the simplest infant module. And then a little bit later, actually quite a bit later, Drin extended this kind of idea to more general exponential functions of arbitrary rank D, and then for more general scenarios. And it's using exactly these construction, or rather generalizations of them, that the Lagrange program for GLN over, I meant function field, sorry, was realized. Okay, and this is due to Drin for GL2 and Laford for GLN. Okay, so these are kind of really fundamental objects for the kind of development of theory of the function field, of function fields. Okay, so that's it for my motivation. Now let's see maybe the actual definition of the infant module. So I need to introduce one object, and these are skew polynomials. What these are is, so if I have some ring here, well, I'm looking at the usual polynomials, but I have some twist, okay, where when I commute a constant a with that's in R, with my tau, I raise a to the qt power. Okay, so this is the only difference with the normal polynomials. So this adds kind of a non-commutative flavor to polynomials. And this identity there, when you want to multiply two general polynomials, kind of distributes, okay, so in the kind of obvious way. And this is how you get the multiplication on all polynomials. But just remember, when you want to pass an a on the left, you have to raise it to the qt power. Okay, and this finally sim lean. Okay, we have done in lean. I'll talk a bit more about the actual implementation in a bit, but here we see that it respects the identity that I showed on the last slide, where importantly, on the left, I have my constant r, and when I want to pass it on the left, then I have to apply some function a certain amount of time, and my function here is raising to the q. So here there's kx. So since I want to pass kx on the right, I have to apply my function k time, and then this is raising to the power k time. Okay, we're almost there. Something that I want to mention is this ring of skew polynomials has another way. We have another way of seeing this as these FQ linear polynomials, a little bit like we saw with the Carlet's module example. We had gotten a linear polynomial. So this we will need to kind of define the action, but we see we get this map here, which is actually an isomorphism. Okay, so this is a bijection, and so for every time you get a skew polynomial, you can also see it as an FQ linear, where the ring for FQ linear polynomials, importantly, the multiplication there is composition. Okay, if you just multiply two linear polynomials together the normal way, you don't necessarily get a linear polynomial, but composition works. And this kind of skew polynomial is kind of a nice way to actually have a ring where the usual multiplication works. And a bit weirdly, I'll write f of x for some f in the skew polynomial. F of x is kind of the image. So it's the equivalent as an FQ linear polynomial. Okay, and finally, this is my definition of the different modules. So I have a field f, matka f, with a fixed morphism from the polynomials into matka f. Okay, so this doesn't have to be injective, but it has to be a morphism. And then what's a differential module? Well, it's just a homomorphism from the polynomials to these Q polynomials. And it's kind of characterized in this scenario by the map from T. So this is the variable of the polynomial. So this is FQT. If you just do the application of your differential module on T, you will get as a constant your hom, and the rest is for some constant, not all zero. Okay, and this defines a differential module in some generality. Okay, so this is actually not general enough for the ambitions of MATLAB, or at least the ambitions of the resource for following. So yeah, and I'll get to that, but pretty much what's the module structure? Well, it's taken by, so this is here a polynomial, and you want to kind of have your action on an element of big F. And what the action is you have your differential module, and then you see it as an FQ linear polynomial. Okay, so kind of have to do this translation, and then you instantiate this FQ linear polynomial with your F from your big field. Okay, so this kind of introduces new actions from FQT onto your bigger fields. And this is the definition that we have at the moment. Okay, so you will see maybe this definition doesn't look too bad, right? So it's actually not too hard to get some definition of different field modules in Lean. The really difficult things that are going on is these two, but the rest is pretty, I mean, we could write it in the 1 hour that we have later, right? But this, having a good definition of skew polynomial kind of took a bit of time, and I think now it's pretty good, but we'll see. And then we have is ring here. This is the generalization I was talking about. This kind of generalize the ring of polynomials so that we can do different modules a bit more generally, not just with an action of FQT, something a bit more general. Okay, and this takes a bit of time. We don't have all the theory on this yet, but we can define it. Just not the theorems, is what I mean. Okay. So now I have, yeah, I'm doing good on time. So what I want to do for the rest of the talk is kind of talk a little bit about maybe less about the mathematics and more about the formalization that I've been doing and some stories that I've lived. So I want to start by something that went pretty well. So this is Ostrovsky's theorem for FQT. So this is a theorem that also exists for the rationals, and it pretty much classifies the possible absolute values that you can have. Okay, so if I define an absolute value with its axiom, so we know what an absolute value should look like. Okay, it should be multiplicative, should have some triangle inequality, stuff like this. Well, you see that it's equivalent to the one I've mentioned at the beginning. So the absolute value infinity, or some absolute value associated to a prime. Okay, so maybe you've heard of the p-adic absolute value. This is something similar, but for function fields. And it turns out we needed to have this kind of theorem for function field to do some proofs. And by the way, the version of this theorem for the numbers was another project that's been done by other people that has been done in MATLAB kind of recently. And now, but we did this version for just for FQT. And this went pretty well, I think. So this didn't take me too much time. So and my impression why it didn't take me too much time is these 4 reasons. There was a good proof script. Okay, so the proof had a lot of detail that I could follow, and I pretty much just followed that proof and it went well. All the definitions of these things were already in MATLAB, so it means that I didn't have to build everything from scratch, which was very convenient. Many of the required lemma that I needed that were cited in my proof script were already in MATLAB, but not all of them, but they were all doable. And there's what I call good API. What I mean by good API is it was nice because some kind of mathematical moves that you do on paper could be kind of replicated in Lean. So usually when you do proofs for FQT, the rational functions, you're going to say, oh, okay, I have some element of a rational function. I want to write this as a ratio of 2 polynomials. And well, you can do that in Lean. Okay, it's no problem. You just call the induction principle for FQT. It writes it as a ratio of 2 polynomials, and then you have a problem in terms of polynomial, which is much easier. Okay, and this is what the proof on paper does, and this is what I do in Lean as well. Something else that I thought was kind of cute. I had a situation where I needed to kind of get this polynomial. So what this says here, it says if there exists a polynomial f of x with some property, here the property is that its absolute value is less than 1, then I can find f prime that has the same property but has least degree. Okay, so it's kind of minimal in a sense. And I would say, well, this is kind of obvious on paper. How do I do this in Lean? And then you think a little bit, well, degrees are well-founded. So you can use well-founded on min from MATLAB to kind of get this polynomial out. And I thought that was also nice because it just follows the paper proof pretty much. Okay, so this is something that went well. Other thing that happened, so I talked about skew polynomials. This wasn't in MATLAB, and it's still not in MATLAB, but we're trying to fix that. And we needed to formalize them. So this is kind of takes a little bit of time, right? You have to take, the idea that we had is to take the polynomials in MATLAB and try to get all the results that can translate to skew polynomial, make sure they're still true for their, for their skew counterpart, and then, yeah, just translate and have exactly the same interface pretty much as polynomials, just adapted. This is, of course, like a lot of work. Polynomials is a huge part of the library, and at the moment, the fragment that we translated is, yeah, 2400 line. One problem that we kind of encountered is polynomials in MATLAB, interestingly, are defined as a structure over unmonad algebra, which is kind of generalizations of polynomials. And then where unmonad algebra are defined themselves as finitely supported functions. Okay, so I was like, fine, I'm just going to copy the structure, copy the theorems, and do it. But unfortunately, in MATLAB, there's kind of a plan refactor to move the structure separation from polynomial to monad algebra. So this means that, well, it would be kind of a losing battle to do exactly the same thing if when this changes for polynomial, we will have to change everything again. So this means that we did something a bit different. We kind of preemptively did the plan refactor. And so this complicated things a lot because it meant we couldn't carry over the proofs for polynomial as directly. We had to reformulate a lot of things. So this is partly why this took a lot of time. But now we have this. So now with this kind of new structure, polynomials are just a definition over skew monad algebra. And then you have a structure over finitely supported functions, which kind of separates and makes it a bit more opaque. Okay, and then, yeah, okay, I have 2 minutes. So maybe one of the last thing I want to mention is that I also find interesting. So when you build these kind of projects, you have results, and you kind of have a decision where you can state them, for example, in terms of rational functions. Okay, but if you do that, you are kind of in a situation where this theorem that you have is only true for this specific object, rational function. But maybe you have some other object which is very similar, it's isomorphic to it, but it's not implemented as a rational function. And then your theorem doesn't apply directly. Okay, so what you do instead is you state theorems in terms of some general k with an instance is fraction ring. And then what this means is that this allows you to use the result for rational functions and also for other stuff that is isomorphic, like the fraction ring of f of x. Okay, so fraction ring of f of x is just you have polynomials. The fraction ring of it is you take you make it into a field. And this is isomorphic to the rational functions. Okay, but if I had stated my theorem in terms of rational functions, I could not use that theorem for fraction ring f of x. So this is kind of a little bit of a pain. So instead, we try to state theorems with these instances, and this means you can seamlessly use results for like a bit more generally. And I have another example of this. So in the definition, we had this is coef ring, which was this generalization of polynomials. We could have just put coef ring here instead of having is coef ring. But then this means that, well, if you want to instantiate it for polynomials, well, you can't do it because you have coef ring. But if you have, but actually polynomials we know are an instance of is coef ring. So this means that we can use Drin modules both in the kind of basic instance of FQT and the more general one with coef ring. So it's kind of adding flexibility and yeah, a design that I think is interesting. And it's not my idea, but I think it's kind of interesting, this design. Okay, and there's other challenges that arise. So there's you have to deal with big towers of fields and do it in kind of a clever way, so things kind of work out. There's some arguments for the theory you can follow quite directly, so you kind of have to modify them in a way that works for formalization. Right now I'm I'm working on a kind of a straightforward way to talk about polynomials in two variables in a way that makes sense for me. So yeah, a whole bunch of challenges, but yeah, it's a lot of fun. And yeah, that's all I had to say for today. So if you have any questions, please ask them. Thank you.
Main arguments hard to follow? Are these actual gaps in the literature or just literature that is obtuse or lacking detail?
So what I mean in this case particularly is sometimes you will have some simplification that the author will say at the beginning of the argument, and it makes sense, but you kind of have to keep this in mind all the way, and then this pops up in proofs because so this is what I mean. It's you can't just say, okay, this simplification is true for X reason. You kind of have to carry this around, and this makes the proof a little bit more complicated. So that's what I mean.
You mentioned the problem of one of the changes that was planned where you had to therefore change it. So as someone who's not used Lean very much at all, how stable, so because this point has come up, like how much overhead do you think this was, and how much overhead in terms of time was this for you? And
doing this. So you mean how much time this took me? That's hard to say, but a bit too much.
Was it a major chunk to just do with the version thing? Like Henning was mentioning the same.
Oh,
that's what I'm concerned.
So yeah, so for me, the versioning is fine. So when version changes, it's not a big problem for me. It's just easy fixes. But this was really the thing that took a lot of time. Is something that should be easy because it's already close to something that's in MATLAB, was kind of difficult because the things that was in MATLAB will probably change a lot. So this is kind of trying to stay close to this. And it's, yeah, I don't see an easy solution because things in MATLAB are still a lot in development, right? So if you try to stay close to their structure, well, what if the structure in MATLAB changes, right? And then you kind of have to adapt to it. And this happens a lot. And you kind of have to decide, okay, do I keep my outdated version or do I do a lot of work to match it and keep it identical?
How much more effort would it have been to fix MATLAB first and then just copying the design from your function?
Much more, I think, because so as I said, this is a fragment, right, that we needed. Polynomials in MATLAB and the things they're defined on, monoid algebra, it's huge, right? I mean, it's a big piece, so I think it's a lot of work. Yeah.
Okay, thank you.